Okay, so let's remember what we did yesterday. So yesterday, basically what we were doing, we're talking about the integers and the various sort of pieces of ways that we could group them, arithmetic that we can define over them. So in particular, we demonstrated that the naturals form do not form an additive group. Right. So what we decided to do instead of using all the naturals or all the integers was take like some of the integers. And depending how many of those integers we take, we get nice properties. So if we just take like the first n integers, then that's going to form a additive group, because that group has, provided that we put a 0 in it and provided that every element has a negative, right? So something like -2, -1, 0, 1, 2, that's going to form an additive group, right? Because if you add any two things in that set, the summation remains in that set. There's a 0, and every number has a negation. If that set also has a multiplication operator defined on it, that's associative, where you have a unit that is like some number that's acting like the multiplicative one, then you're a monoid. And then in addition to a monoid, your multiplication distributes over your addition, then you're called a ring. And what we're going to work on today is demonstrating that the ring of polynomials is in fact a ring. And then try and get all of the same operations or functions that we got yesterday to work on the polynomial ring itself, right? So what did we get? We did addition. Well, we didn't really have to define addition on the naturals or the integers, but we will for polynomials. We didn't have to define multiplication, but we did have to talk about remainders and quotients. And then we did have to introduce the extended Euclidean domain, the extended Euclidean algorithm, in order to compute inverses of elements in their corresponding rings. So that is to say, what we're going to do is work with finitely many integers and a prime number of them, which guarantees we're working in a ring where every member has an inverse, which is actually called a field. Okay, so where we finished off yesterday was talking or not talking about the Chinese remaindering problem. So I just want to open up these slides. Where did they go? One second. Here. Okay, so why am I going to talk about the Chinese remainder theorem? So remember I said in numerical analysis, the problem is working with floats and adding them because the error accumulates. There's the analogous problem in computer algebra is that when we're working with integers that are, or rational numbers or fractions of integers, in order to make it exact, like these fractions can become huge, right? So we don't actually want to work with like all of the fractions. We want to limit ourselves to working in these sort of residue classes of prime characteristic, because working mod p is actually really fast, right? Because we're never going to choose a p that's like in excess of the size of a machine integer, right? These are all going to be the fastest operations that we can do on a computer. Okay, so this begs the question then, like, how do I avoid working with fractions? Like, what is the technique that we're going to use? And that technique is called the Chinese remainder theorem. Okay, so in its simplest form, or in its simplest, stated most simply, it's a game that we play where suppose I have a secret number, and you can ask me what the image of that number is, any sort of modulo. I can say, look, I have a secret number in my head. You say, what is it mod 5? And I say it's 2. And you say, what is it mod 7? And I say it's 5. And then you sort of report that it's the inverse of 3 mod 5. Now, this has sort of two advantages. This means that we don't actually have to work with fractions, right? Because a fraction, when we work mod a prime, is really the same thing as like saying, we don't really have 1/3. We have 1 times the inverse of 3. And we have extended Euclidean algorithm now to determine inverses. Okay, so we don't have to work with fractions if we're working mod p. That's a big savings. And furthermore, if we pick p small enough, these are going to be cheaper operations than the big int operations that you'll be doing in your homework. So one of your tasks actually is to say, okay, here's an example of a polynomial who can only be multiplied provided that we use big ints, and that may be expensive. So if we can now use this on polynomials instead of integers. Why? Okay, so suppose you have two polynomials f and g, and we're going to soon talk about this in greater detail. You can find their product mod 3, right? That's the thing that immediately gets rid of all fractions and make things smaller. So I can find the product mod 3, I can find the product mod 7, I can find the product mod 11, and then I can use Chinese remainder theorem to find the solution mod the product of 3 times 7 times 11. And I'm going to give you a bound to say, look, if the product of your primes exceeds this bound, that you actually found the solution in the integers proper. Right? So this is why we're going to do these Chinese remaindering, because it's a technique that we have for simplifying the arithmetic to make things go faster. Now, if we really wanted to make a very fast multiplication algorithm, because the one that you are using in your project is naive, we would use interpolation, actually. We're not going to do this, but I just want to mention that we can do this because this is pretty cool. If you multiply a cubic by a quadratic, what do you know the product's degree is going to be? 6. So if I give you 7 evaluation points, what will interpolate through that? Or how should I put this? If you have 2 points on the plane, how many lines goes through that point? How many lines go through those 2 points? Exactly 1. If I give you 3 points on the plane, how many parabolas go through those 3 points? Exactly 1, right? So there is exactly 1 polynomial of degree n plus 1 that goes through n many points. Okay, so if I know that f is degree 3 and g is degree 2 and their product is degree 5, I just have to give you 6 evaluation points of f times g. Well, but how do I give you evaluations of f times g if I don't have that product yet? Well, because if you f times gx is the same thing as f of x times g of x. Does that make sense? Right? So I can actually give you 6 points, evaluation points fairly quickly because I just have to evaluate f and g like so. Right? So it's much quicker. And then in addition to that, we'd be interpolating mod p and then using Chinese remainder theorem to lift that. So really, the high-powered techniques would be to do Chinese remainder theorem or its variant called p-adic lifting, which is Chinese remainder theorem, except you're using p squared, p cubed. It's sort of a little bit different in concert with interpolation, right? Where you're just taking 6 evaluations and interpolating through it to get the product. So these are all these Karatsuba is very much like this too, where you're doing an interpolation rather than explicitly finding something. So this is pretty cool. We're not going to have you do it, but you should know because you may not experience very significant speed ups in your code. I'd be surprised if you get any speed up, to be totally honest with you. And it's because everything in your coder is the most naive implementation of all the algorithms, which is fine. So the true purpose of this project, in truth, is for you to work in a code set that you didn't build yourself. That's not good. That like someone screwed up a little bit, right? In fact, the task 2 or 3 is basically like, oh, Joe Blow programmed this and he like programmed it in such a way where he assumed the maximum degree of a polynomial, which is an insane assumption to make. But then your task is to go into, because we're trying to simulate what you should expect to find in industry. You're not going to go to industry and be given a clean piece of paper. You're going to go to industry and be given like a piece of paper that's been marked up by like 100 different people in 100 different ways. So you're going to have to get used to sort of programming in other people's contexts. So it should be a little bit fun. So it's kind of open-ended, these types of projects, and it's simpler than the previous years. Okay, so here's the statement of the Chinese remaindering theorem on integers, which we're gonna later use this to work on products, right? And it's going to be simple because we just have to look at all of the coefficients. Okay, so if I have 2 integers, a and b, and these 2 integers are relatively prime, and then I give you a finite sequence of relatively prime integers called m1, m2, m3. Like I call them m because sometimes this is the moduli of them. And you can find, okay, why a and b? What is this a and b? I don't understand why I put that in there. Okay, so let's just ignore this until I don't even know why. Yeah, that must be a holdover. Could have sworn I removed. Okay, so here's the statement. So I have a secret number u. You can pick as many prime numbers m1 through mk as you like. I will tell you what the images are, mod m1, m2. They are u1, u2, and so on. And then from this, you can recover the original solution. So for example, if I say, I know the secret number is 19 in my head. And you say, what is the image mod 5? I say 4. You say, what is the image mod 7? And I say 5. You can then reconstruct this to get back the answer 19. How do you do that? So the Chinese remainder theorem is an existence proof, right? It asserts that such numbers exist. And clearly, like if someone had in mind the U, there has to be that in mind. So how do we now prove that this exists? Construct it. And what does a construction look like in our setting? An algorithm, effectively, right? So all I have to do is give an algorithm for producing this number, and that suffices as a proof that the thing exists. Okay, and I qualify that as better than existence proofs, because I hate it when mathematicians, like pure mathematicians like me, say, oh yeah, it exists. And it's like, but I want it. It's like, oh, okay, I don't know, right? But it certainly exists, right? It's like, okay, well, sometimes we actually want the things that exist, which require us giving these constructional proofs instead of saying, oh, look, if it didn't exist, then something strange happens. Just, also fine as a proof, but I prefer this type. Okay, so here is the proof. I'm saying this is the number. That is it. Looks like this, and I'll tell you how it was built. So here's the setting. You have this capital M, that's the product of all of those primes that you chose. And I'm asserting there's a unique U between 0 and m minus 1, such that that U is the solution to this problem. And later I'll give you this bound to say, look, if you choose it high enough, then that's properly the solution. So let's just study this U a bit. So what did I say it was? Okay, I'm saying, okay, so U mod M1 has to be equal to UI, right? U mod M2 has to be, U mod M1 has to be equal to U1. U mod M2 has to be equal to U2. Okay, so I've set up this sum where I'm going to solve for each of these V's. So the V1 multiplies by nothing, V2 multiplies by M1, V3 multiplies by M1 and M2, VK plus 1 multiplies by M1 through MK, which means that Vj multiplies M1 through Vj minus 1. Okay, so first of all, what happens if I take this mod M1? What do you get? Yeah, you get this expression. Okay, so I'm saying if I take this whole expression mod M1, we're left with U, like we know, so it's this expression really. So if we take U mod Mj, it just goes to the Vjth term and everything subsequent to that becomes 0. Right? And this allows us to sort of backwards work out the original number. Okay, so I know this U mod M1 is U1. So that's what's here. So what's on the right-hand side if we take this if we mod it by M1? Well, that sticks around, this vanishes, that vanishes, everything else vanishes. So we're left with the expression U1 is congruent to V1 mod M1. So what is U1? V1. Or sorry, I guess that's what is V1? It's U1. Okay, so now we have V1. Okay, what happens if I take this expression mod 2? Well, we know M2. We know U mod M2 is U2, that. What happens to the right-hand side of the expression? Well, this sticks around, but there's an M2 here, so it vanishes, and so does everything subsequent to it. So the second expression says U2 is congruent to V1 plus V2 times M1 mod M2. Do we know V1? Do we know M1? So we cannot, and do we know U2? So we can isolate for V2 like this. We're finding that we're going to have to take the inverse of M1. Can we do that? How? Extended Euclidean domain, right? We know how to take inverses in residue classes, provided that M is a prime.
It's at the M's are all.
Yeah, it's actually, yeah. So the M's only have to be co-prime. It's actually weaker. But if I say that they're all prime right now, it'll just make it easier to sort of understand. When we're working, we will be choosing primes, because that's just, you should build a function that given a prime gives you the next prime. That's one of my favorite Maple commands, actually. I think, does it work? Oh, I don't have Maple on this machine. That's why I couldn't use it. Dear Maple, if you're listening, you're profiting from all of my dissertation. I would like a free copy of Maple if that's... Everyone on this campus tells me that you can get it for free. And every time I try to find it, like it explicitly says Maple is available to you guys online. It's like part of the student, and no one has the key to this. Yeah, it says this is available to students. For the life of me, I can't figure it out. I can download 10,000 copies of Mathematica every day if I want, but I don't know. I prefer Maple. Okay, so this is the how you would actually work out. Like this is a constructional proof that the number exists. What would be left to do is prove that the number that you constructed is actually unique. Right? I'm not going to do it because, well, maybe some of you care, but it's not important to know these details in order to do this implementation. Like when I did this, we had to go through and give detailed proofs of like absolutely everything that's been written on the board, which is why, this course took me 2 months to do, and we're going to give it to you in 2 hours because we're sort of leaving everything as an exercise. This is like, I'm sure you guys love when you see this in your textbooks, right? Left to the student as an exercise. Okay, so here's an example. Suppose we know that U is 2 mod 3, U is 1 mod 5, and U is 5 mod 7. So I suppose this should be U1, U2, U3. Oh, no, sorry. Actually, no, this is perfect. There's a secret number U. It's 2 mod 3, 1 mod 5, 5 mod 7. What is U? All right, so here I'm just going to, I'm just implementing like what I said in that proof. I'm saying here's my UIs, here's my M's. Let's just sort of spin up a vector to use it. To get all of V's, and I'm saying V1 is sort of U1 at 1. V2 is exactly the expression from the sort of lines up where we're using this inverse mod now. And then we can show you, oops. Did I have to go up here? I could have sworn I did this already. Oh, no. This would be the rule of, okay, hold on. Sometimes it gets cranky because of iCloud type of stuff. It's there. It is there. I set this up before I came. How could it have been broken? We'll just give it a second. Because, or maybe I'll just have to restart this. All right, I'll just restart this. Sorry, guys. What happened there? This is the fun part about working with tech. Ah. Let's try again. Cross your fingers. Aha. Aha. Good. I don't need to do that. I think I do this. Will this work? Perfect. Okay. Where were we? Here. Okay. Was it here? Yeah, hold on. Maybe I just need this. Okay, let's just run all of the cells. Is there a command to do that? Okay, hold on. Yeah, I have to do. So here we're all learning together. Run all above selected cell. Is it going to work? 24, 25, 26%, 28, 29, 30.
All above selected
Except for the one that I selected. That's fine. Let's try this now. Hooray. Okay. I love when I get applauses for just working through mild technical problems, but never when I present something that was very hard. My student from 3400 will tell you I got a rousing applause for doing print hello world. All right. It's hard when you're working in a functional language. Okay, so there you go, right? So we found the secret number, right? The secret number is 26, right? So because it's 26 is 2 mod 3, 1 mod 5, and 5 mod 7, right? So you can now do the Chinese remainder theorem on integers. Okay, so the polynomial ring Rx. So now we need to do everything that we've done for integers, right? That is establish addition and multiplication in a GCD algorithm and extended GCD algorithm and Chinese remainder theorem. We need to do it now on the polynomial ring itself, right? Because I'm sort of saying like this is kind of like a different number system. which it will be, but it's incumbent on us to actually define like what the arithmetic is, because it may not be clear. And we were borrowing the arithmetic of natural numbers without explicitly defining it. Okay, so what are polynomials? Surely you've worked with them, right? So it's something like x squared plus 2x plus 1, but not like x squared plus 1 over x minus 1. What is this? Yeah, that's sort of like a rational polynomial, right? From a quotient ring or something like that. Or x sine x. What makes x sine x not a polynomial? Yeah, what category does sine x fall into? Larger category. It's yeah, no, go ahead. Pardon me? Oh, yeah. Well, what I'm looking for is the category of special functions, right? No, this is the thing. All the special functions are those functions that are so special that we give them special names, and they get their own row in the integral tables, right? Because you have to be explicitly told how to integrate them. But yeah, they don't form polynomials, even though it's not a problem in our system to account for them. But we're just going to work with objects that look like this. Right? So if R is a ring, right, that is any number system which gives us multiplication, not necessarily inversion though, and A is an Rx, A is a polynomial, then A has to look like the following. It's going to be an times x to the n plus an minus 1 x n to the minus 1 all the way down. Now, so this is weird now because we can define things which are fine mathematically that don't make any sense to do computationally. So, for example, would mathematicians be troubled by this? Like, would you care if I'm like, oh, like there's an infinite sum of zeros in front of here, like, right? Like this is really 0x to the n plus 1 and plus 0x to the n plus 2 plus 0. So mathematicians would be like, yeah, I don't care. There are an infinite amount of zero terms in here. I am not troubled by that. Why would that be a problem for us programmatically? Yeah, we don't have space for an infinite amount of zeros in the system. It's wasteful to store any zeros. Actually, we'll talk a little bit about dense versus sparse representations, right? So if we just say, look, the very first one here, like, has to be non-zero, that sort of sorts it, right? Even though that doesn't necessarily in between prohibit explicitly zero stored terms, this just makes it so that there has to be a finite like number of them. You don't get to put a front stack your polynomial with an infinite amount of zero terms. Okay, so we're just going to agree that, well, so here's some nomenclature. Okay, so A is the polynomial, X is called the unknown or the variable, AK is called the coefficient, XK is called the monomial, their product is called a term. So a polynomial then is just a sum of terms, right? Polynomial, many monomials, right? Stuck together. That's where the term comes from. That the degree of this is going to be the largest n for which an is not zero, or the leading coefficient, and the leading term is an times x. And so surely you're familiar with terms like degree and leading coefficient and leading term, yes? Perfect. What should the degree of what's the leading coefficient of the zero polynomial? I think that's sensible, right? What's the degree of the zero polynomial? Well, here's a problem. How many zero polynomials are there? Is there a zero polynomial with this provision? No, actually, right? So like this is kind of strange, right? So it's when we're programming like sets for which there is not a unique zero, that always messes things up, right? Because you want to be able to detect if something is zero. So this begs the question, like, how should we represent the zero polynomial? Is that the absence of terms? Is that like the sum over the empty set or something like? So we'll sort this out like when writing, and we're effectively going to say the zero polynomial is a polynomial of a single term, which is has coefficient 0 and degree negative infinity, right? That's how this is actually defined, because 0 is special. So what's the degree of a constant, like 7? zero, because it's monomial is x to the 0. So 0 is kind of special in this in our definitions because it creates a lot of problems when we start programming these things. But the mathematicians don't care, right? 0 is 0 to them. Okay, so the degree of 0 is minus infinity. So just you start cataloging all of these edge cases into your head because these are the things you're going to have to be concerned about when programming. A lot of bugs I've seen from previous years is people allowing multiple versions of zeros to exist, right? But we can be smart about how we set up interfaces to outright like make it impossible for a user to define something like that. Okay, so here's the representations of polynomials in the project. Now here's something funny. Okay, so we have polynomials, and that's going to be sums of terms, right? So we surely should create maybe a structure for terms, and the struct for terms should hold the coefficient and the degree. Agree? Do terms, are they closed over addition? No, right? What's x plus x squared? That's a polynomial, right? So are they closed over multiplication? Yes, they are. Yeah, like x times x squared gives you x cubed. Each of those things individually are a term. So isn't it strange that we found some type of set which is closed over multiplication, but not closed over addition? So just, yeah, keep that. It's kind of strange. You're going to have to be careful about how we utilize this because we're not going to actually be able to define term addition. It's not closed, but term multiplication is going to be fine. Under what conditions can we define term addition? If they're the same degree, x squared plus x squared gives you 2x squared. Okay, so they can be combined. So, but addition isn't closed over terms are not closed over additions, but terms are closed over multiplication. Generally speaking, multiplication is going to be easier for us to define. Why do you suppose that is? What is multiplication if not repeated addition? So addition may take some time to work out, but then multiplication is like, just call that like recursively, right? I am just repeated that. And actually the addition is going to have a little bit of takes a little bit of thinking. Okay, so here's a term. It's a structure. It has a coefficient. It has a degree, and it has this like funny inner constructor. Right? This is how the term generates its smallest form. This is basically going to say how do you. It's going to prohibit the user from creating things that are impossible. Right? Because if I didn't put this inner constructor there, you could just spin up a term that was like 0 minus 8, right? And that's bad for a variety of reasons. We're not supposed to have zeros on our terms. The degrees have to be positive. So that's what this inner constructor is going to do. It's going to say when user tries to construct a term, it's going to go to this inner constructor. And before agreeing to actually provide this term, we're going to check the degree is positive. If the degree isn't positive, we can't do it. That's an error. Otherwise, check the degree is non-zero. If the degree is non-zero, no problem. Here's your new term. If the degree is 0, or sorry, if the coefficient is 0, what does that mean? User is trying to construct a 0 term. Okay, but we need to make sure that we're going to construct the same 0 term each time. So let's just designate the 0 term as the term with 0 coefficient and 0 degree. Even though maybe we should put minus infinity degree there, but does Julia have minus? Probably. It would just be max int. But anyways, these are all design decisions. It's not to say that one design decision is better than another. Probably now that I'm looking at this, I don't know. No, because you can't put minus. The degree is technically minus infinity, but you're still putting 0 times x to the 0 into the polynomial, right? So I think I just convinced myself that this is fine. But the point of the inner constructor is that we're just simply not going to let users create terms that are bad, that are ill-formed, right? Unless they break the abstraction barrier. Have you ever heard this term? So nothing stops a user. Oh, in this case, yes, because their structs are immutable by default. Okay, so we'd be safe in this case. But you could tell term to be mutable, right? And then a user could simply say, oh, term.degree is now minus 3/2, right? You can bypass the constructor. And we'd say, look, everything's broken, but that's your fault. Like we told you how to construct terms here through this constructor. You reached through the abstraction barrier and did something. You're not even supposed to know about the inside of this. Okay, because we're going to have to be working at all levels. We are going to create the abstraction barrier. Like this may be new, right? Because we're going to create functions that are going to have to be utilized by other people. So we have to give some thought about how we want people to utilize them. But we also give thought about what happens underneath the abstraction barrier, because these things have to be implemented by us, right? So we do have to say, okay, a polynomial is going to be a vector of terms, and bad stuff can happen, but the user is not going to realize that. Cool. Here's a way that we can construct the zero term. I forget what this is called, but 0 is in base, 1 is in base. So we can sort of add this by saying, oh, catch this. If you want to construct a 0 for type term, it's this 0, right? So instead of, when we program, instead of saying term 0, 0, what we actually want to do is use that 0 constructor. Because in the case we change our mind about what we want the 0 to be represented by, it is safer for us to do the latter, because all of the changes will propagate. The same is true for 1. Okay, so what we can do now, and why is this? I think that was should be deleted. I can't click. Oh, here. Ignore this. I think that was a question from last year. We failed to remove it. I hate how this moves around. Okay, so I'll just load this into the system. Okay, so we have a struct for terms. We have an inner constructor for that term, so we can't create anything or instantiate anything that's ill-formed. And if we want a 0 term or a unit term, we can do that. The 0s and 1s are important to define, right? Because don't forget, we're trying to form groups and rings, and these groups and rings have to have features like this. Okay, so here's the struct for a polynomial. And actually, there are various ways that we can represent polynomials. So let's go back here. So in an earlier version of this project, maybe years ago, like one of the things they had to do that you won't have to do, but I still want to mention, is that we had them swap out the representation of a polynomial from dense to sparse. So here's what a dense representation is. So here's a polynomial of degree 5. What is one obvious way that we can encode this in a computer? Well, it's like spin up an array of 6 boxes, and we'll say this is the box. Okay, I know we're not 0 indexed, but let's pretend we're 0 indexed, right? So the thing here, the first one, we're going to say designate as the coefficient to x to the 0. The second one, we're going to designate as the coefficient to x to the 1. 3, we're going to designate as the coefficient of x squared. So something at position k is going to be the coefficient for something of k plus 1. And this is perfectly fine. This also makes adding super easy, right? Because you just put the vectors beside one another and you add them. You just pack the shorter one with zeros, right? Because this is the least significant, or this is the constant, and this is the leading term. Right, so if one is wider, it doesn't matter, because remember I said you can always pack an infinite number of 0 terms at the front of your polynomial, right? So super easy to implement, super fast addition, but what's the problem here? Big, right? Okay, so we actually have to work on, later on we'll be working with polynomials called cyclotonic polynomials, or they look like x to the power of p to the power of k minus 1. Working with those polynomials is going to be of critical importance to our factoring algorithm. So how many terms does x to the power of p to the k minus 1 have? 2, right? Like the non-1 term and the 1 term. Okay, so how many zeros are we going to end up packing in x to the p to the k? And usually we're picking like not small p, like we're choosing p to be some 32-bit prime number, which then itself has to be taken to an exponent, right? So you're talking about that, yeah, to store 2 things, like I'm going to have to spin up an array of mostly empty space, okay? And this is a disaster. This is a disaster, spatially at least. Right, so there's 2 ways that we can represent polynomials. One of them is densely, and that comes with a bunch of benefits like easy addition, but has downsides like being really spatially wasteful. Or we can omit zeros, but then other things become hard. Like then in order to find a term of certain degree requires searching. Like if I wanted to know the degree 7 term in a dense one, I'm like, it's at position 8. That's where it is. Whereas here, you have to like go through the whole list. But you don't normally have to do that. you will see as I define most of the arithmetic on the polynomial, there's like one operation which is important. Can you guess what it is? Pardon me? That's our ultimate goal. But in order to do addition, we're going to have to do something. We're going to have to look at our polynomials and extract parts of them. So if you're adding f and g, what's the first thing that you do? But you normally do so by descending down them, right? So you'd normally look at the leading terms of f and g, right? And ask if they have the same degree and merge them if they do. So what I'm saying is that you don't ever really need to look at the whole polynomial. You really only need to know its leading term at any given time. And I'll show you that the arithmetic is effectively all defined by being able to extract a leading term and being able to remove that leading term. Did any of you know what a heap is? A heap is effectively a way of putting a bunch of values into a binary tree so that it's very fast to insert something into it and remove it. And it has the property that the largest thing is always at the top of the tree. So if you take a heap and you put monomials into it and you sort it by degree, what's going to be at the top of the heap every time is the leading term. You get that constant time. And then to remove it is a log operation, right? So if you were to do this project, what we're asking is, hey, take the dense representation in the project, swap it out with a heap, and you should see some like pretty big spatial gains, right? So I wanted to mention it because in my discipline, this is there are whole laboratories dedicated to one style or the other. So I happen to come from the sparse world, right? Because system solving is sparse because we require these cyclotonic polynomials. But otherwise, things can be dense, right? There's a toggle in Maple that will switch from one to the other when it realizes it. Okay, so the way that we've programmed polynomials into this project is using the dense representation, right? So spatially wasteful, but a lot of things will then become easy, like addition. Even though we didn't, the way that I'm going to show you the algorithms is presuming it's going to be agnostic to how you choose to represent it, which is better. Okay. So this polynomial is going to be a zero-packed vector of terms. That's just how I showed you on the slide. The terms are assumed to be in order. Yeah, I don't know why this doesn't word wrap. Okay, so let's just, who cares about the comments? You can see them, but it's going to be a polynomial is going to have an attribute. It's going to have called terms, which is going to be a vector of terms. We're going to have to maintain an ordering on terms to make sure that the term of degree n is at the nth plus 1 position in here. Okay, so this is an inner constructor that tells you how to create a new polynomial. What is a new polynomial? Well, the new polynomial has to be a zero polynomial. What should we designate the zero polynomial as? Well, the list of one term, that is the zero term. Okay, we could have done it so that the zero polynomial is an empty list. I'm not saying that's invalid. I'm just saying that's not what we chose to do. Like this is going to help us avoid some edge cases. All right. So here's the inner constructor of a polynomial. So if you want to create a new polynomial that's just not the zero polynomial, so this is going to be for us, the programmers. If a user were to use this, this would be breaking the abstraction barrier. We do not want users to use it. I'll show you what the interface we created is so that users can create polynomials. But so this really is for you, right? We're going to take in a vector of terms. We're going to filter that vector, those terms for zeros, because people can do funny stuff. They can like put multiple zeros into that term vector, and that will screw up. So we have to sanitize it a little bit. And then if everything in it happens to be zero, then you've been asked to create the zero term. Otherwise, okay, so we have these things here, right? This is the thing that you have to do in your project. And it's actually like you really only have to find like 3 or 4 lines of code and remove them. Like that's in effect, like you just have to remove this here, really. Yeah, really, that's all you have to do. And there's some free marks. You just remove that line, but then you have to find all the other ones that also do this, remove them as well. Because you see, this doesn't really have any effect on what's being constructed here. It's just sort of some arbitrary thing that happens. Okay, so you look for the max degree among all of your terms. We are assuming that it doesn't exceed the max allowable degree. And then you put all the terms into a sort of ordered matrix like this, right? Where the ith position is going to hold the term of degree I plus 1. Now update based on the input terms. Yes, so this now is making sure, right, that we're doing the insertions, right? So this is creating a new vector of all zeros. This is now taking the thing that we brought in, right, this vector, and actually putting them in their appropriate positions into the vector. Okay, so this now begs the question. Yes, sir.
Wouldn't the ith one be degree I minus 1 since we're starting from 0? So the first one actually relates to degree 0 instead of 2.
Plus 1 accounts for 1 indexing.
Like for the first.
Oh, no, this makes sense, right? The term of degree D will be at position D plus 1, won't it?
Yeah,
Yeah.
I understood what you said. You said that the I would be the and would be referring to the I minus 1. But
Sorry, it's because this language isn't zero indexed, and that drives me crazy. Like my brain is set to default 0 indexing. Okay, so I'll sort this. Julia is a 1 indexed language. Okay, so the term of degree D will be at position D plus 1 in that matrix, right? Which is why I hate 1 indexed languages. Because if this was 0 indexed, I could say the term of degree D is at position D. And it would correspond exactly with the natural number. Julia changed this to a 0 index
when
language.
you're talking about matrices, then it's like, oh, okay, that's row. This is first row.
Yeah, I was confused with like if you want row then column or column then row. I never know. Look, I'm a pure mathematician. Like all my arithmetic is going to be off by 1 or 2, and that's fine. You shouldn't care. It's in the ballpark, right? I shouldn't be expected to actually have to do arithmetic. Okay, so if we're not going to let users construct polynomials via this, how are we going to ask them to construct polynomials? So we're going to do something quite clever. I'm going to construct something called the x polynomial. And I'm going to say that x polynomial is the polynomial of that has one thing in it. It's term 1, 1. And what's this going to allow us to do? How do I get a new cell here? So if I say something here like x is equal to x poly, okay, I get that. Okay, I'm eventually going to define addition and like multiplication and other things. So if this is defined and addition and all these other things are defined, I should be able to do something like, like this if I eventually want to. Right? Because this is these one polynomial multiplied against itself to get the squared multiplied by a integer 3, right? So as long as I tell Julia, this is how you multiply polynomials. Oh, and I guess I shouldn't even say 3 isn't a polynomial, even though it's reading as an integer. But this is how we're going to have our users interface with polynomials. Like they're not going to be able to build stuff that's weird. Let me show you something like this. If you can try to build something weird, I can say, oh, give me x squared plus minus 1 times x squared. This is something that you're going to have to fix. It's not currently working. I have to do this. Right? This is pretty cheeky. What have I typed in here? X squared minus x squared plus x minus x. Like, what should we produce in this setting? Right? Because we're forcing the user to engage through this interface, they're actually being prevented from doing any funny business because they're being forced to just build a polynomial using arithmetic, right? Not by like giving us some type of vector. We're saying build it like you're actually a mathematician. Okay, so if at any point they were to use the polynomial constructor directly and do something screwy, we say you broke the abstraction barrier, like all guarantees are off. Okay, so now that we have that, I just need to show you how to do addition, multiplication, remainder, quotient, and extended GCD, and then maybe Chinese remainder theorem 5 minutes. You ready? We're obviously not going to be able to finish it today, but I'll show you addition. And then multiplication really can be done in 30 seconds because it's just repeated addition. Okay, so we talked a little bit about addition. And what did I say? Well, you have to look at the leading term of f and g. And if they're the same degree, you merge them. Otherwise, you just pick one of them to be the new leading term, right? So here's some pseudocode. This isn't Julia code. This is sort of higher level because the idea is you should be able to take this and implement it in any language that you want. So I'm saying, you give me 2 input polynomials that have integer coefficients, and I'm going to output a plus b definitionally. Do you understand what that means? I'm like, you can't verify this. I'm saying this is the definition of addition for polynomials, right? And then we could, after this sort of try and prove that this is closed and has all the properties that it needs. We won't, but we can if we want. Okay, so what do we do here? If the degree of A is equal to the degree of B, that is, their leading terms have the same degree, then merge them. Okay, but isn't this funny? I'm defining addition with other type of addition. Okay, but what addition is this addition? On terms. That's a lesser addition. And when did I say terms can be added together? What's the precondition? That they're the same degree. Isn't that what the if statement is asserting? Okay, so we enter this if statement. We have a precondition that the terms do have the same degree. So go ahead and combine them. This will be easy. Just add their coefficients together. Okay, and then you call addition. Then you add this term, right, to the addition of what remains. Remove the leading terms from A and B and recurse. Okay, so this is why this is agnostic to the representation of it, because I'm not saying move pointers down, even though in this setting, that's what the dense representation, that's all that would be required of you, right? Move the pointer down 1, like forget that the leading term is there, or even none of this would even be necessary because you would just add the vectors together and be done with it, right? But if you if you swapped out your base representation for sparse polynomials, then you'd be screwed. Then the dense method, the adding vectors wouldn't work, right? So I'm saying, look, as long as you have an interface into your polynomial which gives you leading terms, that's it. We can define everything, no matter what representation you're using. Okay, so this is what happens when the terms are equivalent. This is what happens if the degree of A is bigger than the degree of B. You keep leading term of A, you remove it from A, and then you just recurse. What happens if degree of B is bigger than degree of A? Well, you do the opposite. You take the leading term from B, and then you add it to the addition of A with B less its leading term. Now, since we're calling these things recursively, I said the most important thing here is to ensure that what we're calling is smaller than what we initially had. Is that the case? Or is A minus the leading term of A smaller than A? I would say so. How about B minus the leading term of B? Yes. Okay, so both smaller. This is smaller. So all parts here, we're making a recursive call on objects that are smaller. And there is going to be some... What happens with the base case? Yeah, no, this is... It will force... No, but eventually everything will be the constant, right? Yeah, eventually it has to be this case. And then, but I still need to say addition of 0 and 0 is 0. Okay, so I'll have to think about that actually. But I think probably, yeah, there should be some, yeah, if A is B is 0, or like what we mean by 0, then like return 0. Well, I'm not sure. I'll have to think about it. Which addition? Oh, every branch calls addition again. Yeah, so there's no terminating procedure here. Okay, yeah, so sure, yeah, geez, I bottomed out. Yeah.
A bit of a recent notation to allow, like, to define equality on the integers such that 0 polynomial is equal to 0.
Is 0 integer?
Yeah, so like on one side, like define.
I wouldn't, because they're not equal. Like it's the same way that 0 the float isn't equal to 0 the integer. The values are, but the representation, like so I guess that means it depends what you mean by equal, right? In this, Because in my 1001 class, I would say 1.0 and 1 are different. Like 1 is an integer, 1 is a float, and that difference is important. But mathematically, they're not different. So it's kind of, yeah, I don't know how to answer your question. You can choose to abuse notation that could confuse users. That may be the downfall. Like I certainly wouldn't expect to compare 0 with the 0 polynomial and that report true. I don't actually know what I would have it. Because I would expect 0 to be promoted to a polynomial, the 0 polynomial. And then then you'd compare 0 polynomial with 0 polynomial, and that I'm comfortable saying is. But even saying are two objects from different, like disparate sets, are they equivalent or not? It's kind of like they're from different sets. How can they be equivalent? They're not even occupying the same collection. So I don't know how to give, there's no yes, no answer to that. I can only give my argument as to why I wouldn't do it. Okay, sorry, I've already kept you for a minute too long. Let's just look at the actual Julia code that implements addition, and we'll continue from there next time. So what did I just need to define addition and maybe the negation operator, because I was doing subtraction. But remember that a group is obligated to have additive inverses. And that effectively means everything has to have a negation. Okay, so how do we do this? So how do you add a polynomial and an integer? So if you have P a polynomial and N an integer, you just promote the term, you promote that integer to a term. Okay, and what happens if you want to do an integer to a polynomial? It's the same thing, it's just the opposite direction. Okay, so we have polynomial added to integer, integer added to polynomial, and now we just have to define what it means. This is what it means to add a polynomial to a polynomial. What I now need to what remains to be defined is how to add a polynomial to a term, right? Like I just want to take this and glue it to the front of another polynomial. So given P a polynomial and T a term, since you want to produce a new polynomial, that's why we're going to do a deep copy here. Like properly give me there's a version of this where we can destroy this by adding T to the end of it, but I don't think I want to destroy previous calculations that I've been doing. But again, this is a design decision. So we'll copy P. Okay, so this is sort of old code, like because push is like heap notation. So for push for you just basically means add append goes to the end, right? Right. So pushing here is essentially appending to the end of your list. And it's just otherwise, if it's the biggest thing, it just puts it at the back. If it's not, it just sort of you have to search the list for the appropriate place to put it and merge it when appropriate. That's effectively what's happening here. Which is, yeah, because like we get the dense representation, we get to index, right, as much as we want. So finally, so we did term and polynomial. So we did polynomial and term. What about term polynomial? Well, cool. They could just flip the input. Right? We don't define this again with things reversed, because now you're maintaining two code sets. And finally, how do you add two polynomials? Well, if you give me two polynomials, P1 and P2, I will just duplicate P1. And for every term of P2, I will add it to P1, right? Because we just defined how to add one term to a polynomial. So we can just do this repeatedly. Now, this is the world's worst addition algorithm, okay? Because I said all you had to do in this setting was add like 2 vectors, which is very quick. This is like some aggressively maybe quadratic operation, right? So I'm not saying we're building the best computer algebra system. I'm saying we're building a computer algebra system. It's like what we would do after this, once everything is working, if we were smart in our programming and everything was modular enough, we start going in and then sort of speeding up various parts, right? So we get someone who's going to dedicate 6 years of their life to making addition on monomials fast. Okay? And you may laugh, but I dedicated 2 years of my life to doing that. My master's degree is specifically on polynomial arithmetic, because when you're adding monomials and comparing them and multiplying them as the basis of everything that you're doing, if you make that a little bit more fast, everything becomes more. It's really fun playing at the kernel level of software packages, because any speed ups you get there propagate to everything, right? So anyone in Maple who uses polynomials, your code is faster because I made that faster. Okay, so no, please no more applauses. Oh, at least, yeah, that was actually worthy of applause. Okay, so here's how you showing that the arithmetic works. We'll talk about multiplication next time, but it's effectively. I'll let you go. I'll let you go. Okay, I'll see you next time. Chats. I abandoned you again. I hope everything went okay. That yes was from an hour ago, though. You guys still around? Oh, okay, cool. Yeah, thanks. Everything technically worked out today. Cool beans. Okay, stop sharing.